Hi, my name is In Jang from the University of Manchester. I'm happy to have this opportunity to give a talk about this work in Roman 2021, which is about omnipotent virtual giant for remote human swarm interaction. There are lots of industrial needs in remote inspection and maintenance using robotics technology, particularly for industries involving hazardous and extreme environments such as nuclear, oil and gas, space industry, and etc. Within RAINHub project, which stands for Robotics and AI in Nuclear, our colleagues have been looking at using mobile robots for radiation inspection at nuclear contaminated environments. In the near future, many of these robotic inspection tasks could be done by using teleoperation or semi-autonomy. However, eventually these tasks will be done by having many number of fully autonomous robots that can collaborate with each other. And yet, we believe that practically at least a single human supervisor is required to achieve guaranteed operations in terms of safety and performance of these multi-robot systems. Then, naturally, we can come up with a question such as how can a single human supervise lots of remote robots efficiently? To address this question, in this work, we propose a concept called Omnipotent Virtual Giant. Actually, this concept was inspired by my childhood memory in which I was interacting with a group of ants by changing their positions and environments. For example, I was simply picking a couple of ants and placing them another place, and I was putting a stone in their existing path in order to change their moving behaviors. From the ant's point of view, I might have been considered as a supernatural being. As similar to this, in order to interact with a swarm of robots, how about being a supernatural giant in virtual world? Let me talk about its details with some assumptions for our near future. Let's assume that we have a swarm of autonomous robots which are deployed for remote inspection or maintenance missions in a dangerous environment. The robots are supposed to address these tasks collaboratively thanks to decentralized decision-making controllers, even though each robot can only have local perception and local communication capability. The information about its robot status and its surrounding environment can be transmitted to a control tower and rendered as a virtual reality for a human supervisor. The human supervisor is wearing a VR goggle and can see what is going on in the remote site through the virtual reality. If necessary, the supervisor can intervene the robot's behavior by giving individual command and swarm level command or even environment level command. Even in this futuristic scenario, we can still think of some challenges in terms of how this human supervisor can be able to understand the remote environment and how to provide appropriate level of human intervention, particularly with consideration of the large number of swarm robots. Basically, for human swarm interaction, we need to have two interfaces. First, the human supervisor should be able to understand the status of swarm robots in the remote environment. Also, the human should be able to provide appropriate command to guide the behavior of the swarm robots. In terms of the perception interface, we should be able to know each robot's status, which we call individual level perception, but also we should be able to know overall situational awareness, which is the macroscopic understanding about the swarm robots. In terms of control, we should be able to give an individual level command to each robot, which we call robot-oriented control, assuming that the robots are following a particular swarm behavior. We also should be able to give a command to the swarm level. Another thing is that as the robots are autonomous, maybe it is more efficient and better to provide virtual environmental change, which may guide the robots indirectly, rather than giving explicit and direct commands, which are actually overriding their autonomy. So in this work, we now show that by using Omnipotent Virtual Giant, we can implement all of these required interfaces for human swarm interaction. Our work uses virtual reality with Leap Motion, which is a hand tracking sensor. In virtual reality, We can be an avatar in a giant form as well as in a miniature form. When we are being a giant, we can have overall situational awareness. On the contrary, when we are being a miniature, we can have individual level perception. And we can change these two perception modes by changing the size of the avatar like this. By simply pinching and gathering our hands in or out, the operator can change the size of its avatar in the virtual reality. The operator can also fly over the virtual world by simply closing hands and moving them around. As an example of robot-oriented control, by simply picking a virtual robot to a destination place, we can give an individual level moving command to each robot. Secondly, we also implemented an example of a swarm-oriented control interface in which by flipping over our hands, there will appear a purple-colored cube, and by placing the cube into a place, the robot follows to the cube by keeping its circular formation behavior. Lastly, after switching to draw wall mode, the operator creates a virtual wall by pinching and dragging to a certain direction. If the wall is there, then the robot changes its direction according to its collision avoidance behavior. We also demonstrated all of this with real robots. At the remote site, there are small-sized mobile robots, and their positions are being tracked by a low-cost camera tracking system called Wycon. And this laptop communicates to the robot and connected to another laptop at the master site. The remote environment and status of the robot are rendered and shown to the operator through VR. Let's see our demonstration. So by simply picking and place its robot, the robot moves according to the operator's command, like this. And this shows the swarm-oriented control that we implemented. By changing the position of the cube, we can control the swarm's position. Here, the swarms are following a circular formation controller as their swarm intelligence. And using virtual walls, we can indirectly guide that robot without overriding its autonomy. Here, the robot is stuck there, even though there are no real walls in reality. But when we remove all of the walls, then the robot becomes free to go according to its autonomy. We can also have a mixed reality environment where we can exploit few of real robots for hardware testing, but also with the simulated robots, we can also test how much the large number of robots provide psychological burden to the human operator. So naturally, we were wondering the overall evaluation of the proposed method. So we recruited 10 participants and made them guide 50 robots into 3 task areas according to the task demand. Particularly to evaluate the effectiveness of the environment-oriented control, each participant was allowed to use pick and place only for a condition and can use pick and place and virtual together for another condition. We recorded the completion time of each mission and the number of interactions made by the participant. The result shows that using pick and place and virtual wall together required less interactions because virtual wall can block the entrance of a task in the arena when it becomes containing the required number of robots. But interestingly, this strategy took a longer time than using the pick and place interface only. This seems to be because changing interface modes for virtual walls took some time. Overall, the participants agreed that the proposed methods are fun to use and intuitive and useful to interact with swarm robots. For conclusion, we proposed a novel concept called Omnipotent Virtual Giant for human swarm interaction and showed that the proposed method has potential in being intuitive and easy to use for swarm robotics in a remote site. For the future work, we should conduct more rigorous usability tests as we were not able to do so due to the COVID-19 situation, unfortunately. And also we need to consider the communication topology of a true decentralized swarm robots and information passing priority to minimize the latency between the operator and the robot.